That's
go.
what it needs.
Now it's
It
on.
needs the on switch.
It does. Okay.
Yeah.
All right, everybody, good morning. Nice to see you all again. Looking forward to a really great semester of talks. As a preview, next week, Wes Warren is going to talk about how we can tell from large-scale genome sequencing uh, if and when cats were domesticated, or maybe they domesticated us. So before we get started, everyone please silence your cell phones. And I don't see any, but they're starting to get very strict about food and drink in the auditorium. And no, you don't count. And they're talking about kicking people out if you bring in the contraband. So please don't bring coffee and donuts into Monsanto. So today's speaker is Dr. Neil Fox from the Department of Atmospheric Sciences. So Neil grew up just outside of London and then got his undergraduate degree from the University of Manchester in physics because he said he figured physics left a lot of options open instead of specializing in something right off. He took a detour when he taught high school science in the Caribbean and then came back to England where he did his PhD in atmospheric physics and then a postdoc, edging a little bit more into atmospheric sciences. And so he says he just kept on drifting in the direction of atmospheric sciences until that was what he finally, as a biologist, I would say you were finally differentiated as. And then realized when he started looking for faculty positions that there are a lot more jobs available in atmospheric sciences in the US than in the UK. And so he started looking for jobs here, and this is where he's landed, and so this is where he's been his entire career. And I guess what he's going to talk about today is more of a interesting side project. He says he normally does, you said, radar. And so let's please welcome Dr. Fox and give him our attention.
Thank you, Dee. Oh, that does work. I actually feel quite honored because you didn't mention that as part of this semester's series, you, of course, have George Smith coming up. So I feel...
No, you're the headliner.
Exactly. I'm the headliner ahead of George, which is a fantastic position. I feel incredibly honored. But what I'm going to talk about today, you may remember, we had an eclipse. It's actually almost exactly the 18-month anniversary. That's how long it takes me to process my data. So 18-month anniversary of the total solar eclipse that came through here in August 2017. Were you all here for that? Did anyone miss it? They went out of town and kind of like, you did?
My mom died.
Oh, that's okay. Okay, so a big event around here, obviously, and right across the nation. We put together a team because we were so well situated to look at some of the effects of the eclipse. And the part of it I'm going to talk about today is a project where we distributed a bunch of temperature sensors to whoever we could find who would take them, hopefully young people interested in science, to try and get a really fine-scale observation of how the temperature varied as the sun was eclipsed. So the next thing I'm going to ask, this is like a big thing, did anyone here participate and get one of the sensors? Excellent. Well, you'll get a big thank. Oh, it's Stacy. I didn't see you there. Hi, Stacy. And you did as well, back there, Jeff. Okay, you're the only one. Okay, you'll get another chance to be thanked later on. Okay, so there's a lot of thank yous to be handed out, which I'll actually do throughout. Actually, I didn't even mention all the other contributors. I did all the work. All these other people on here just came along. Jeff, do you want to? Jeff, who's the second author, who was actually the principal investigator on the project, is sitting at the back there, and none of the others look like they could be bothered to show up. But hey, they've probably heard all this before, and a couple of them are from quite a long way away. Okay, so the primary thank you I have to give, well, not the primary, but I'm contractually obligated to thank NASA, who actually provided the funding that bought the sensors and allowed us to do the deployment of those. Everyone else who needs thanking will come later. And also, part of the agreement with NASA when they funded was that I should give some kind of public presentation of the results. So this is me fulfilling my contractual obligations to that. And you get to put up with it, so thank you for showing up. And there's the eclipse. That's what it looked like. It's all seared in your memories as kind of, that's it, we can stop, we've seen it. Okay, so some background. Again, most of you hopefully would be familiar with this, but this is the track the eclipse took. It crossed from west to east, right across the country. And one of the notable things is that here it points at the greatest eclipse duration being kind of down toward the boot heel, maybe just over into Tennessee or Kentucky. Kentucky, I guess that is. I can't see my own map. But the color of this center line represents the duration of the eclipse. And you can see that as it passed through Columbia and this area, mid-Missouri, we had some of the longest durations, over 2.5 minutes. And that provided us, we thought, with an excellent opportunity to take some really good observations and to get other people involved in the process, whoever, like I said, would get a sensor. So, next up, it's not moving. Oh, yes, it is. So, just a brief word. There are, of course, they're not common total eclipses, but when they come along, people get excited and they get a lot of observations. So there have been a lot of previous observations. It's only recently, in the last few decades, that those observations have started getting more precise and more scientific in terms of the impact on the environment of the eclipse. So, for example, there are previous eclipses that have been studied where the temperature drops during the eclipse, which is what I'm going to focus on mostly, have been in the order of 1 to 3 degrees Celsius. So 2 to 5 or 6 Fahrenheit cooling. And there's some other studies people have done. So obviously this went right across the country. People were looking at it wherever they could. So some of the other reports I've seen were from Wyoming, where they saw a 4.6 or 9, I guess, Fahrenheit drop. And that was where they had a slightly shorter duration of eclipse. They had clear skies. And then in Tennessee, which is probably close to that maximum point, they had a 4 degrees Celsius drop, or 7 or 8 Fahrenheit, but they had cloudy conditions. And if you have the cloudy conditions, you're not going to get the heating up before the eclipse that allows the temperature to drop so much. So what we were interested in, or what I was interested in, was whether we would see similar temperature drops to have been seen previously, and then use as many observations as possible to build up a picture of how the temperature changed across the area, and try to get some of you guys involved in helping with that observation to try and encourage people to think not just about, wow, isn't this a fantastic natural event, but kind of think what it means scientifically, how we can investigate these kind of effects and what impact they could have on the environment around us. So there were quite a lot of projects going on looking at the different aspects of the eclipse and how it impacted wildlife and so on. But what I'm interested in is simply the temperature change during the eclipse. Thank you. So, oh, I always do this. I say what's coming on the next slide. I'm ahead of myself. So as I said, the primary objective was to get this map of how the temperature changed across the area. And one of the reasons I got excited about this, again, it's an eclipse, what's not to get excited about, but the timing of the eclipse for us here was unique. And it was unique in that not only was it happening in the middle of summer, when we would have these really high temperatures anyway, so we might see, we have the potential for a big change in temperature because we would expect the temperature to be quite high. It was also, we were close to the area where the eclipse would last the longest time, so something of the region of 2.5 minutes of totality, giving more time for the changes to be felt. And most crucially for this location is it happened very close to local noon. So all of you will remember exactly the time it happened. It was about 1:27. But we're on summertime. The sun doesn't actually follow summertime. So natural time was actually 12:27. And we're a little further west than where that would be. So you end up calculating really close to the maximum elevation of the sun for the day, was when we experienced the eclipse. So we could expect from all of that whole combination of factors that we might actually see a really big temperature drop. And I remember that I gave an interview before the eclipse. I can't remember who it was to. And I said that I wouldn't be surprised if we saw 10 or 15 degrees Fahrenheit drops, which haven't been recorded before. But that's what I said, because I thought, hey, let's go for it. And I told some of my colleagues, and they said, rubbish, never. But I was expecting big temperature drops. I'm optimistic. This was my previous, so some of these previous eclipses, this should have come in before that one. So my previous eclipse experience looked like this. I thought I'd put this one up. I happened to be in England, back home, on in March 2015, when there was a 90% total eclipse. And this is what I saw. Because it was England in March, and all you get is like thick grey clouds. So you couldn't even tell there was an eclipse going on. When it finished, I thought it might have got a bit brighter. Hard to tell. It was like 9 or 10 in the morning as well, so it wasn't even that bright. But that was as close as I had come to being in an eclipse, and it was thoroughly underwhelming. So I was really looking forward to this one. Okay. Oh, what? Help! What did it do? Go back. Giving it all away. Go back. What happened? No, I've broken it. We're stuck. Here's some nice pictures of people's yards. It's stuck. Don't know. We'll bash it. That's all. Oh, yeah, that worked. See, I was right. Bashing it. No, bash it again. I don't know. Getting ahead. Oh, that worked. Okay, here we go. This is where we are. Sorry about that. Okay, so this is the path of the eclipse. As you can see, here's the center line where we would see the maximum duration going through, and you can see that it passes just south of Columbia, so that's where we would expect to see the biggest effects right along that blue line. And our idea was to try and distribute sensors kind of through this area. And as you'll see, we got out as far as Marshall, and we got down south, somewhere down in here was our furthest south. So we covered quite a lot of this line through mid-Missouri with sensors, well, not covered. And just a quick aside, so prior to the eclipse, I had one of my grad student classes model what they expected the effect of the eclipse to be. So here I'm thanking 4 of my grad students who I stole some of this stuff from, Chastity, Russell, Jane, and Kevin, of whom Jane is still around. And I also thank them because they, amongst them, particularly Chastity and Kevin, I remember, did quite a lot of driving around delivering sensors to various people around mid-Missouri, which saved me a couple of trips to Centralia, which isn't so bad, but I had to do other things. So their model was based on a pattern of overlapping circles. So this is kind of a very crude cartoon model of how the eclipse works. The yellow circle represents the sun. The black circle represents the moon. And both of these progress kind of from southeast. So we see the eclipse track actually coming from the west, northwest to the southeast. But the way it works is that the sun, of course, is coming from the east and catching up and overtaking the moon. So it kind of looks like this, and then it does two at once. So the way we model it is by calculating that overlapping area to see how much of the sun gets obscured. When we do this, we get, so this is the incoming solar radiation. This is what we would expect over the course of the day. So solar radiation at sunrise is 0 watts per meter squared, gets up at that time of year to something close to 900 watts per meter squared at noon. And if we model the overlapping spheres, we can actually get that down to 0, although we haven't calculated the exact time. So we would take this nice V shape and impose it, take it away from this curve, and what we actually saw during the day looked like this. So these are radiation measurements from not net radiometers, solar radiometers measuring the incoming solar radiation from 4 different sites. Thanks, Jeff. And you can see that they kind of follow. There's a bit of wiggliness with some light cloud in some of these areas, but you can basically see that V shape. The one that has a tighter V comes from Tucker Prairie out towards Kingdom City, west of here, east of here. My directions are terrible. East of here, and that one has a narrower V because that was further from the center line, so it had a shorter duration for the eclipse. But we see that actually on the day, so this is radiation measured actually on the day in Central Standard Time, not daylight savings time. We see that radiation from the sun going to 0 right at that just after noon time. Here's another, I just throw as many pretty pictures. So this is satellite imagery of the event, and you may be able to just make out the shadow of the moon as it goes across. So this is satellites observing the surface, and that big black blob that runs across is actually what the satellite observes being reflected by the Earth. And as the moon passes across, it just casts this huge shadow over that. For those of you who are super excited by actual meteorology, other aspects, you can also see that as it goes through, it kills off a lot of the clouds down here, which lose the solar energy that's forming the convective storms, the thunderstorms down here. So the shadow passes over, the storms get depressed because they lose all the energy, and then a bit later they all pop back up again when the sun reappears. So, exciting stuff. Okay, what else we got? Oh, we can also see, I should point out as well, that we did have some storms in our area, and actually we had a similar effect. So to the north of us, we had this cloud that just impinged on the north of the area we're interested in. After the sun came back, we developed this line of storms that was kind of trying to form before the start, but didn't quite get going, but then it got going after the eclipse. So again, up towards Centralia, they saw some of this. Okay, let's get on to this. So the data sources, I'll get on to the meat of this. So the data sources, the primary one I'm going to talk about for this is these things called I buttons. These are what we distributed to as many volunteers as we could find. We also had the Missouri Mesonet, a network of automatic weather stations that we could compare this to, just to check that our observations from these little I button things matched up to kind of the more official record. We also had the USDA eddy flux covariance towers, which are these very high-tech, complex weather stations that measure all kinds of stuff that I'm not going to talk about today. If you want to know more about them, Jeff at the back can answer that. And also the Ameriflux Tower, which is situated down toward Ashland, which is a tall tower which is there to measure carbon fluxes, other biofluxes. Again, takes very high quality, detailed meteorological observations. And you can ask Jeff, well, Steve's here as well. So we had some access to other data that we could control. And one of the interesting things about this, again, is so we had the green Oh yeah. So the crosses represent those locations of those towers. So that's up near Centralia. This would be Tucker Prairie, and this is down in Basket Wildlife down in near Ashland. And we also were launching radiosondes, balloons with instrument packages. One here at South Farm, again at Centralia, and one here. Was that at your house, Stacey? No. I thought that was one of the plans. Hey, everyone shows up. Again, we had this extra data. We're looking at it. I'm not going to talk much about it, but just lots of supplemental data, as much intensive data collection as we could measure or we could gather during the event. Okay, so the eye buttons, they look like this. So they're not that big in real life. They look kind of big on there. They're low-cost temperature sensors, and we compared them with things, and there's one hiding in here somewhere. There it is. I'll actually pass this around, and Jeff has another one. So I have to break it. It's too well constructed. So that's the actual size of the thing. And we pack it into this shelter, which is designed to protect it from the direct solar radiation, but allow ventilation to keep it from heating up too much. So I have one here, which I'll pass around, so you can have a good look at this. And Jeff has another one at the back that he's going to pass around, just because it's a prop. We'll use some props. And again, I want to thank my students, Paula and Russell, who built these by hand with great loving care and tenderness, and a nice template they got off the internet. And so they came from a template. They were all identically made and then distributed to the volunteers. Okay, what's next? I don't know, what's next? So within the eye buttons themselves were set to record data every 2.5 minutes. So because they're small, they have very limited memory. So you can either get them to take a lot of measurements over a long time by spacing out the measurements, or you can kind of do them more frequently over a shorter time. And we chose this resolution, this timing of taking a measurement every 2.5 minutes, because that gave us about a week of measurements with frequent enough measurements to capture these variations in temperature we were trying to get to. And the idea of doing it for a week, so we could have just done it for the day of the eclipse and done it every 10 seconds or something like that. That seemed like too much fineness in the timing. What we wanted to do was to capture a few days either side of the eclipse so that we could compare the record from the eclipse day to similar days either side. So if we had, hopefully, 1 day or 2 days before or after the eclipse, which was cloud-free, so we could see what the temperature variation was when there wasn't an eclipse, and compare that to what happened on the actual day. And we distributed 51 of these to various people. Some of these we took ourselves. 49 were returned. I'll come back to that. One had excellent data, but was not consistent with the rest of the sites. I'll come back to that as well. One where the placement was not well done, and I'll come back to that as well, so I'll describe all these. And then 6 that were in place for the eclipse, but weren't in place on the 19th of August, so 2 days before, which is the important date. So as it says, they were set to start recording on the 18th. It turned out that the 19th was a beautiful, clear day for good comparisons, but we had 6 of them that weren't actually in place on that date. So I have some beautiful temperature recordings from the trunk of my car, which don't really tell me too much. So the volunteers were identified in many ways. The main way was through 4-H, and this is where I give my super extra special thanks to Kay and Shannon, who went out and worked through the county offices of 4-H to identify volunteers and get these things out to them. And without their efforts, this would have all been, they would have all been kind of scattered around Columbia by university faculty, which wouldn't have been that interesting. I did use some of my faculty colleagues, because they lived in interesting places. There were also some that ended up in the hands of teachers, either by accident or by design. So in particular, one went to Paxton Keeley, which was my daughter's school at the time. So I went to her homeroom teacher, Mrs. Schmidt, again, I would like to thank. One went to Hickman, to his close. One ended up at Midway Heights, and one at the Catholic school. And there may have been a couple of others that were actually at schools, but I wasn't told that that's where they actually were. And of course, getting them into schools is great. That, again, exposes them to more kids who will be able to kind of see what's going on, get involved in scientific observation. So the idea was that the installation was done by the volunteers themselves. So they got sent or were delivered one of these sensors. A lot of them, or quite a number of them at least, went to considerable effort, because they would drive to their county 4-H office, which, I don't know, I've driven to some of these county 4-H offices, and it can be 30, 45 minutes away from the other end of the county. So there were people who went to pick up their package and take it back after the eclipse and would drive to their county office to do this. So some considerable efforts by quite a lot of these volunteers. They came with a set of instructions, a couple of free pairs of eclipse glasses, just to keep people's eyes safe, because we always have to be aware of that. And the instructions were to place the sensors kind of at standard meteorological instrument height, which is between 1.2 and 2 meters above the ground. And of course, you know, not many people have their own tripod that they're ready to set their weather station on, so they found some very ingenious ways of setting these up. The idea is you want it in an open area, so again, you're ventilated, no shading from trees or buildings, so natural environment in place 3 days before the eclipse. And if possible, I asked them to send photos of their installation. Partly this was so I could check if I got some strange data, whether it was to do with how the volunteer had set the thing up, but also just because I wanted to see what these things look like in place. So So again, so the biggest thanks of all go to Kay and Shannon of 4-H and all the people who volunteered. That's you again. Because without the volunteers, none of this would have been possible. Okay, so we're done. Okay, so here are some examples of how I expected them to be set up. This is the perfect setup because this is the one I did myself. So in my backyard, with the help of my daughter. And I should really be embarrassed by the nice really bin that's kind of lying around, so we'll skip past. So this was kind of how I envisaged people would get to do it. People have chain link fences, whatever. But, so that's my, oh, actually, so I had some, no. Okay, all right, no, we'll go back to that. So that's fine. So these are some other examples of what people did. So this one, every time I looked at the photo, confused me because I keep thinking it's mine, but it's not because my neighbor doesn't have a shed like this. But it looks absolutely identical, the fence and all this stuff around it. So they were obviously following the good example. Here is the badminton net option, the ladder option, and the tetherball option, which I think is particularly good, unless you actually want to play tetherball, I guess. And then this is another one I set up on, which I had spare, so I put it out somewhere else. So lots of ingenious ideas. These ones I really like, because these are, if you see are any of these yours? No. So these are, I really liked because then they're a great example of perfectly out in the open, nothing around them, isolated, high up, good ventilation, everything's great. So these were even better ideas than mine. So mine was perfect, of course, and these are even more perfect. So this is the helping out the birds one, I guess, which is fine unless the squirrels get there, I guess. And with added dachshund in the outside. Keeping an eye, I guess the dog is there to keep the squirrels away so that they don't interfere with the observations. And so this is the one set up outside Hickman, which you'll recognize. And this is Mrs. Schmidt's class at Paxton Keeley there's the sensor on the fence right there. So lots of different ways of setting it up, lots of ingenious solutions. Okay, so this is where they ended up. So this is the map. Again, even though we're trying to spread them out around the surrounding counties, obviously we still end up with a whole load in Columbia because we have a lot of enthusiastic people. There's just more people around to spread them around to, but there we go, that's the distribution. The ones to note, so there are two, all the numbers and letters represent kind of codes, the kind of serial numbers on the sensors so I can match them. The two yellow ones are the ones that didn't make it back. So this one belonged to Jeff, who's my principal investigator, sitting at the back. Didn't return his. One of two. The other one, they did actually try to return, so this one up here, but it had developed some kind of bug infestation and had to be disposed of before it made it back, which was a shame because it would have been nice coverage. But So the only person who actually lost their sensor, okay, we'll leave that. Okay, and over here there's a expansion of kind of how you can see the distribution. So if you know where you live, you can find your closest sensor and match up. So this is kind of more of the Boone County distribution. Okay, so how are we doing? So the actual data, when it came back, we downloaded it from the sensors and plotted it out using the software that the sensors came with, and it's gone crazy. Oh no, what's technical support? I just finished, yeah, thank you. I don't know, we'll try and start it again. Maybe I'll, what's it doing? Yeah, it's there. Mm-hmm. Okay.
The schedule is not printed out right now, but it is available on the Saturday Morning Science website. And you can also
It's out of
stream
control.
a lot of last semester's talks as well as this
Did
one
I do that?
from the
It's gone
LS
mad.
YouTube channel. And both of the addresses for those are in the email that I send out every week.
Right, can we open it up again? Turn it off and on again. May as well.
Where did it go? Where's it gone? Where's it gone?
Oh wow, it's sitting.
Computer's gone nuts. Okay, solution. I could do my laptop. Yes?
Wait, you have it on your laptop?
Yeah.
Yeah, do that. That'd be great.
Okay. Okay, just bear with me. See, as a well-prepared, experienced presenter, I always bring backup. And hope the backup is charged. Maybe. One of these. It's a pretty old laptop, so pick a hole that looks like HDMI. I'll put it down and then you might be able to do it. Yes.
Anyone have any questions?
Well, yeah, is it? Oh.
I appreciate the pure science aspect of this project and the public cooperation. I'm wondering if there's any practical consequences. What if you had only found 1 degree of rise, or what if you'd found 15 degrees of rise? Well, what would that have meant?
That's a good question. I would have to be honest with you. In terms of practical value to atmospheric science or meteorology, I'm not sure there is a huge kind of scientific discovery that gets made from this of great value. From just the temperature, we did some more detailed observations of how the biosphere, how the plants react, how some of the development of the exchange of carbon dioxide occurs. That has more value and is more interesting because what we get from that is effectively a very accelerated kind of sunset, sunrise process where we're compressing that into a very short period and seeing what the response of the environment is to that. But Jeff, do you want to So he did more of that stuff. Maybe we'll, if, um, okay. Yeah. Okay. Thank you. That kept us all occupied while we did this. Okay, so back to the show, I guess. So this is one sensor. This is what the raw data looked like in terms of temperature against time. And so this would be the 18th of August, the 19th, the 20th, and the 21st. And you see this big dip, V-shaped notch in the temperature record. And if you compare that, so we picked the 19th as a comparison day because you see this almost smooth temperature response, what we would expect on a clear day. And we also see this in some of these other days further on, but the 19th, the starting temperature is pretty close to where we were on the 21st, so we can do some direct comparison of these 2 days. Well, that's the idea. Oh, I can't advance with this anymore. I have to actually do this. This is the plot of all of the sensors. This is all of them on the 19th. And you can see how they all follow a pretty similar shape. A couple a bit cooler, except for this one in the green. And they should match, the colors should match. So here are the same things for the 21st. And again, this green one is outlined, but they all follow this beautiful kind of shape where you see the effect of the eclipse. And in terms of the temperature difference, we can eyeball from here, somewhere dropping from around 32 degrees Celsius to 26, 27 degrees Celsius. But it's hard to see because we've got a whole load of lines all on top of each other. If we overlay, go get back to used to this. If we overlay the 2 days one on the other for an individual's location, this is what we get. So here again is for the 19th, actually starts off a bit cooler and follows this nice curve. And then the 21st, again, we get this big dip. And so this is pretty typical. As you can see from this one, they all follow that very similar pattern, except for this green one. And we could also compare to one of the more official, professionally maintained sites. So this is the one location where we put the iButton sensor on the same weather station as that. Yes. In this location, yes. So in Centralia to the north, we had storms move in, clouds came in, and we saw some cooling. So good spot. Preempting all my big things. No, that's. So the thing here is that we're getting a very good match between the iButton sensor and the kind of So the iButton sensor that costs us a few dollars each, and the professional temperature thing that costs a couple of $100 or whatever it costs. So very good agreement, so we can have some confidence in the quality of the data that we're getting from these. But I also mentioned earlier on that we had a couple of locations where we had problems with the installation. So this is one of those. This is installed, I shouldn't really call this a problem. So this is installed on the Ameriflux tower. So as you can see, up above the forest canopy, where you get a completely different temperature response to when you're near the surface. So although we got some great data from this, incorporating it into the whole record doesn't make sense because it would be inconsistent with the other sites. The other one is this one, which was kind of that green line on the previous one, where we see this big spike in temperature on the 19th and another big spike on the 21st, but after the eclipse. And this one stood out as having poor data. Fortunately, I was able to investigate this and ask the person who'd installed it how they'd installed it, and they'd actually put the whole thing upside down. And I should point out that this wasn't one of the 4-H volunteers. This was another faculty colleague, a science professor who really should know better. Not an atmospheric scientist, I'll point out, but a professor who has their office just down the hallway from me, and they put theirs upside down. And so, so this one, again, we couldn't really use the data, and I'll show you, I think, the difference between. I still can't use it. I've got too used to using the button. This is the answer to your question. You got there too early. So again, so these are two sensors that were placed further north, and most of them, as we saw before, so the more typical ones, oh, they're right back here. No, right back here. We had the drop from the eclipse and then a recovery to a similar or higher temperature later in the day, as we'd expect, kind of around 2 or 3 in the afternoon. We would expect that the temperature to get back up. But some of the locations to the north, Centralia, and I think out towards Marshall, and we have one up in Glasgow, they had more cloud move in, and you didn't get that same temperature recovery, so you get this dip, and then it doesn't get back up there because of the influence of the cloud. Okay, so now we're getting to the actual measurement bit. So there are 2 ways to measure what we would call the temperature drop due to the eclipse. One of which I kind of call this shoulder method, where we have kind of the 2 shoulders between the dip, and we're measuring how much the temperature decreases from the morning maximum to the minimum during the eclipse, represented by this red arrow. And then we can have the comparison between what we might have expected the temperature to get to, which we observed on the 19th, given a cloud-free, eclipse-free day, and again, what the temperature dropped to during the eclipse. And most of my results, I did both of these, but most of these come from more of this shoulder method, which is, again, what other people have done when doing this in previous observations. So I still can't do that, so I need to press buttons. So again, I mentioned this already, so you're measuring the difference between the morning high and the eclipse minimum, restricting the times you're looking for these to particular hours, and ignoring transient effects, so clouds or anything like that that pop up. We can't pull those out. Or there's, again, the daily comparison method, where we compare the 19th, which we identify as a clear, good day, to the eclipse day. And the problem with that is that you would have some offset of the timing. So in that case, I chose to use the time of the minimum observed on the day of the eclipse with the same time on the previous day. But as you saw on that previous example, there was a little shift. The temperatures at the start didn't line up exactly, but it gives us some idea. So now we get into some examples. So this is an animation showing the temperature variation over the area on the 19th, which is what we would typically observe. And so the time is up here, and you can just see that through the day, everything warms up. It keeps warming up. Here's my temperature scale. This is in Celsius, so we're getting up there. This, of course, is Columbia, so the urban area heating up a little more than the surroundings, and there you go. It just keeps heating up and then cooling down as we get into the evening. Nothing particularly exciting. If we do the same thing for the day of the eclipse, firstly, you can see we have a larger area because we had a few more sensors that expanded the domain we were looking at. This is going up through the day, and then when the eclipse starts, here comes the cooling effect. This is exactly the same color scale as we had on the previous one. And then after the eclipse, it all warms back up again. We'll run through this one more time. So again, we see the early morning warming prior to the eclipse, and then the eclipse approaching, bringing this cool down with it, passes right through the area, gets us right down to this 25. A bit of extra cooling where we had some more clouds up here, and there it is. So, moving pictures. So next I'm going to show a couple of static plots of what we can pull out of this. So this is plotting the comparison of the 19th to the 21st, so the day-to-day comparison. And here I'm plotting it as a function of longitude. So this is the most westerly, which would be Marshall, and this would be the most easterly, which was somewhere southeast. I can't remember the location. And this is the magnitude of the change. This, I think, is all the sensors. So this is the one which went with this plot. So 11 degrees Celsius drop from one day to the next, because that peak from the upside down actually maximized right at the time of the eclipse. So we got this huge drop. Again, we see other big drops over in these more westerly areas, where again, the temperature on the 21st was suppressed by some extra cloud cover. So the temperature on the 19th got particularly high in these areas. So these are not very good representations of the actual temperature drop. This one down here would be the Ameriflux tower, the one up on the tower, which shows a much lower drop than anywhere else because it doesn't have the effect of the heating from the ground that all the others get. So more realistically, this is a plot in order of size of drop, temperature drop from maximum, from the shoulder method, from the morning maximum to the time of the eclipse. And so these are just plotted in ascending order. And the mean temperature drop by this method across all of these, again, excluding the two where the data was inconsistent, was 6 degrees Celsius or 10.9 degrees Fahrenheit, with a couple of locations getting 7-degree drops and a few 5 degrees. So pretty consistent right across. Everywhere between had a similar drop within a couple of degrees Celsius, so 3 or 4 Fahrenheit of each other, which gives me a lot of confidence that actually this is real, believable data. If we plot, ooh, that's doing funny wiggly things. Oh, that's nice. Okay, so this is, for some reason, got some speckliness going on. This is the temperature drop day to day. This is including the upside down sensor and the tower sensor, which were actually very close to each other. So this is where the upside down sensor was, and this is where the tower is. And you can see, no, this would be the upside down sensor because it's blue, and this would be the tower. And you can see that by leaving those in there, you get this huge, weird dipole thing of temperature just from having these two extra sensors in. Whereas if you take them out, you get a much more reasonable looking field. And this again is the temperature drop comparing the 19th to the 21st. So we see these larger temperature drops, and again, far greater drops generally in the north and west, where we had more cloud cover on the 21st. This is a really ugly way of plotting it, but I thought I'd put this in. So this is just to illustrate. So of course, what we have is a bunch of point measurements. And all those previous plots I've just showed, the nice animation and that smooth plot, are made up of these. This is what happens if you basically take the point, and for every point around it or every point in the area, you just find the nearest temperature to it and plot that. And you end up with something like this. So it's all disjointed. So those other ones require some kind of smoothing or interpolation of the field. And this is typical in a lot of sciences, but in atmospheric science, meteorology, where we generally have a lot of these point measurements and you have nothing in between, then you have to do this kind of smoothing or interpolation of the field to retrieve a more reasonable field. The one thing that this does allow us to do is identify, so this is for the shoulder drop, the location where we see the greatest temperature decrease. And it's right in here. So that point, that sensor right in there, which relates to this whole area, is where we saw the greatest temperature drop. And I'll tell you where that was in a little while. Oh, no, I won't. I've got it here. I'll do it from there. So that is right in the kind of Hartsburg Prairie Home area. That's where the biggest temperature drops were seen. And I'll explain why when we get there. So if we do the interpolation of that previous map, we smooth this. So this is now a single smoothing or interpolating the actual minimums. We get something that looks like this. And again, so blue is the biggest drops. Again, right in there's the biggest. Some of this stuff to the north, which had some cloud cover. And also, I should point out, there wasn't just cloud cover. The storms to the north put out these cold gusts. So some of that temperature decrease was also due to cold winds being produced by those storms. So some of that happened as well. And kind of this cluster is, of course, the Columbia area. And if you want to know exactly, you are about there. Because we have a sensor just across, somewhere around here actually. So that would be where we are now, which means this area in here would be kind of downtown Columbia, and this area which didn't cool down so much would be kind of West Columbia, I guess. So we're seeing some kind of urban effects. This would be kind of around Ashland, and this again would be Hartsburg and Prairie Home over here. What's the next one? I don't know. Whoops. No? Oh, what am I doing? Pressing too many buttons. No, I'm not. There. And that's just, I made it bigger for some reason. So again, downtown Columbia, West Columbia, area affected by cold outflows and clouds from the storms, Hartsburg and Ashland. Okay, we're almost done. So what the extra sensors allowed us to do is observe some of these finer scale details that would have been difficult just using our standard observation network. We get all this extra spatial detail by adding in all these extra sensors, thanks to all those wonderful people who agreed to put one of these in their backyard and help us out. And on top of that, what we got is possibly the biggest temperature drop ever seen during a total eclipse. So a potential world record right here, well, in Hartsburg, where the drop was about 7 Celsius, greater than 12 degrees Fahrenheit, which was remarkably similar to what I predicted before the eclipse that everyone thought I was crazy to predict. But hey. I was just going for extreme numbers that are kind of. The thing about this particular point, I think, is that if you remember back to the very first map I showed of the eclipse path, this was really close to the center line of the eclipse. So it had the maximum effect, the longest duration, the greatest time of totality, and all that other stuff. And they also had clear skies, so it allowed the warm up in the morning, allowing the contrast between that and the totality of the eclipse to have its maximum effect. So, well done, Hartsburg. You now own an unofficial world record. When I publish this, we'll get it out there. Oh, that still doesn't work. So, this is my last slide. So, again, most of the sites saw so Hartsburg got the biggest decrease, but it wasn't extreme compared to the other sites. So I actually have pretty good confidence in that because a lot of the sites got more than 6 degrees Celsius temperature drops, which means that a 7 degrees Celsius drop seems reasonable. And we saw some of these urban effects, the effects of the cloud cover, the cold outflows from the storms, and we couldn't have done this without the participation of these enthusiastic and willing people who volunteered to do this. And as I said, some of them went to considerable efforts to go and get their sensors and return them and do that. So again, a final thanks to all the volunteers, especially Stacy, because she turned up when no one else did. And that's it. Thank you.
All right, if you have any questions, please raise your hand and I'll bring you a microphone.
No one has questions. I guess so.
Very concise.
They were stunned by the...
All right, well, let's have another round of applause for our speaker.